smart capabilities. Next. This is our breakdown of our outline of our project. We started with project motivation and summary, system description and related theories, moving on software and hardware system design and implementation, testing, iterations, completion. We also included a demonstration video, cost analysis, and we will conclude with code of conduct and ethical considerations. Next. I will now present our team. We have Showa Oyakawa. He's our project manager, and he's also a software engineer. Derek Lam, he's our software lead. Ayat Saidan, he's our hardware lead. And myself, Andrea Toro Merchant, I'm a hardware engineer. Next.
So the technology has been improving over time in like any kind of environment, and it's the same in the classroom environment. We started off with the chalkboard, and then we went on to the marker board, and currently we're now in the time where people are using smart boards. And smart boards, however, are very expensive. If you look at the Leo building, there's not many of them. There's mostly concentrated on the basement area that is newly constructed. So as an alternative, what some people do is they use a marker board conversion kit, which changes a marker board into a smart board. However, these things often create silos where the use of the marker boards and smart features are completely isolated and separate. So if you use it as a marker board, you would use a marker and then write on the board. But if you want to use the smart capabilities, you have to put that down and we'll have to use a specialized pen. And what's even more egregious is when you try to convert a chalkboard into a smart board, what typically would happen is you would put a white wallpaper-like material that's going to be pasted right onto the chalkboard to be allowed to use the smart capabilities. But then if that's done, it completely renders the board unusable as a chalkboard. So what we want to do is we want to reimagine the chalkboard as a teaching tool by adapting smart capabilities, which will enable educators around the world. So the modernization will be done through two key factors: digitization and smart capabilities. And digitization is simply, it's going to pick up the image from the chalkboard, apply image processing, and save it, so which can be saved afterwards, so it can be sent to other students after class. And the smart capabilities are, we're going to be doing it is what you're going to be able to use the computer right on the chalkboard by interacting with the IR mesh that we're going to have on the chalkboard. The impact we hope to have is improved environmental impact. So by enabling the use of chalk over plastic markers, so less waste. And we're trying to remove the headache of using markers because, as you know, professors were having like bundles of markers thinking at least one of them will work, ending up using every single one, none of them work, and they'll have to run out and find another one. That's kind of wastes everybody's time. And chalk and chalkboards are also readily available anywhere around the world. So it will also impact a wider range of populace. And also the uniqueness is there is no product like ours in the market because everything else typically is centered around the marker boards and none addresses the chalkboard issue. Our system description will describe through our data flow diagram. The first part will be the touch interaction. The user will be able to interact with the IR mesh that's going to be on the chalkboard, which the Arduino picks up as coordinates. And then that's going to be sent, the coordinates are going to be sent to a computer that's going to be attached to it, which will then replicate the touch, whether it be the left click, right click, or double click. The other aspect of it will be the digitization. So the user will be able to trigger the camera to take a picture. Then the picture will be sent to the image processing program. It will be cleaned up and then will be sent back to the user to use however he wants. Derek? Sorry, my screen is a little collapsed right now. So I will cover it in place for now. So the software theory is we will be using for image processing, we have used the Fentang algorithm, which is the adaptive binarization method, which was proposed by Dr. Feng and Dr. Tan during the 2004 IEEE conference. And this is based on maximizing the local contrast for the image analysis. This is done through the use of local mean, local minimum, standard deviation for data to separate the text from the background by shifting the primary local window. And to compensate for the effective illumination, the dynamic standard deviation is used and the secondary local window to calculate a local threshold value seen by the formula down below. And then and then by using this threshold, we'll be able to determine in a binarized way if there's a black text or a white background. Derek, can you
Very good to
speak
see
now?
you.
Yeah, can you see me now? Because I was like presenting, so I thought like you are like seeing me and hear my voice.
Sorry, I didn't hear you. All right, so do you want to do anything else you want to cover here?
Yeah, just go to the next slide. So as you can see in the left side the picture, so you can see there's a small window. This is used to like calculate the local mean, local medium, and standard deviation to separate the text and background. And there's a secondary local window, a larger window, to comparisize the effect of illuminations. And after a whole stuff, you will having a binary image, and the right side, you will have a pseudocode of the whole code of algorithm. Next.
Infrared emitters use gallium arsenide and aluminum gallium arsenide to produce infrared light, which relies on the energy band gap of the element. The energy band gap is quantified from multiplying Planck's constant h and the speed of light c, while dividing by the wavelength. The infrared sensors use a threshold lens that collect infrared light from emitters, which is directed into the power electric plate to activate the sensor, dividing the signal output by the product of the incident power and detection active area. We can find the responsivity of the sensors.
So for the first design is the image process for our software side. We assume like to capture the board, and then we have a click for a camera, and then we will transfer the image to a raw data, and we will try to have first image processing, which is the image inversions, and then we will convert to grayscale. After extract the image components, we will do the image segmentation by using the Phantom algorithms. And also, we will try to flip the image because in our setups, the camera is upside down. So the image, you can see that it previously is also upside down. So we'll try to flip the image first, then we will try to do a skew correction to correct the angle between the board and the camera. And we will try to reduce the noise to have for the salt and pepper noise after image segmentations. After that, the image will be projected and can be stored in our desktop. Next.
So for the touch implementation, we are using multiplexers that is running across the board, which is going to pick up the signal and it's going to be sent to the Arduino, where it's going to be processed into a single coordinate. And the coordinate is based off the number 00 is based off for us for the bottom left. However, Windows, you treat the upper left pixel as the 00. So we would have to convert that to something that Windows can use to properly replicate the touch manipulation. The use of the typical Windows.h library will allow us to use the execution of the clicks very easily. And we had to come up with a system to be able to differentiate. Is it a left click, right click? Is it a double click? So we implemented a 4-clock cycle to have that logic of the mouse interaction type.
So the last design of our software is the GUI. We're using the Qt creator to create the main window. You can see there's a two connection and disconnection button, and we are using the threads to touch for the touch interact loop and break it and to connect with the Arduino with the touch systems. And for the other buttons, open cameras, close cameras, capture, snap, and image processing, it is for the camera operation for the capture of the image and image processing. And after hold that, you can be the image can be saved in your local desktop.
The emitter circuit was developed by achieving 1.2 volts and 20 milliamps in each emitter. So by calculating the resistance needed to obtain those values, we got 180 ohms, which was used to drop the voltage from 5 volts to 3.7 volts and feeding 1.2 volts and 20 milliamps into each emitter. The sensor circuit is powered through our anode, which is supplied by Arduino Mega 2560. The signal outputs of the sensors are connected from the cathode leads to the multiplexer input pins. In addition, the picture on the left is an implementation of both the emitter circuit and the sensor circuit combined to make a single hub. The hubs are collinear so that both the emitters and sensors are facing each other. The outputs of the multiplexers are then connected to the analog pins of the Arduino. The picture on the right is a representation of the 2x3 expansion that consists of 5 hubs. A simple example of how emitters and sensors work is like a TV remote, where pointing the remote to the TV's receiver and pressing a button sends a signal. But in our mesh, our emitters are always on, which allows the sensors to remain at a high state until a sensor is blocked, which represents a touch interaction at the user's end. One of the biggest drawbacks we had was power distribution in the emitters. The power was attenuating between breadboards due to the additional internal resistance of the breadboard. We implemented 2 solutions. One was by creating a new path of least resistance, which instead of internal connection in the breadboards, we soldered the ends of the resistors with a thin wire, and we also introduced a second power supply to deliver enough power to each emitter circuit.
So the integration testing was a little bit difficult because we were not all co-located at the same time. So the initial integration we've done was on a smaller scale. So as Ayad was showing earlier, for the one by one hub, so we used that as an X and Y coordinate, and then we were testing the touch interaction, the serial communication that will send that coordinate to the computer, and the mouse movement where the mouse cursor movement will be replicated on. So we were successful in implementing it. However, there were some jitter in it due to some serial communication with incomplete data that was causing some errors. So we implemented 2 solutions in regards to that. And on the software, on the Arduino side, we were sending some extra data that we weren't needing, such as I was using parentheses initially to replicate a coordinate system. But since that is really unnecessary, that is only for human purpose, I cut that down to 2 numbers for the X and the Y coordinate. And also on the computer side, we were using error handling. So if we did end up getting some corrupt data, to just drop it and go on to the next read. Sorry. And then when we went on to the integration acceptance testing, we integrated the whole 2x3 hub, and we also integrated not only the touch but also the image processing. All the expected results was achieved. However, in regards to the touch interaction, there were some issues with consistency. We went back to it, made some further adjustment to the alignment for the diodes to ensure the IRs were pointing toward the IR sensor, and IR emitters were pointing towards each other, and also a realignment for the software so we have like the proper voltage reading, but it will still require some more fine tuning. As for our project, we went for the waterfall method that kind of like met with each other. So we were working separately for the hardware and software, and then when we were complete, we completed the prototype and started the testing in regards to that. And as for the iteration, the 1x1 hub, we actually had a simple problem where we had too much power going to a single resistor in a serial parallel setup. So we had to like modify that, redesign that to a parallel system. As for the Arduino touch processing, which was working in parallel with the touch interaction, as stated earlier, there were some alignment issues that was causing some varying in the voltage level. So it required some realigning. As for the 2x3 hub, as he had stated previously, we did have issues with the power supply not providing enough power, and also the breadboard providing resistance. And then, as he was stating, we did the solution of connecting direct connection as opposed to using the breadboard for the connections for some of the rails, and also for using an extra power supply. And for image processing, initially we had some issues with the chalk dust residue that was being picked up, and we tested various algorithms to denoise. And for the touch interaction, we required additional logic, because before it was just moving the mouse. We required additional logic for different click types. And as for the GUI, the integration touch was running on an infinite loop. That was the thing that Derek was talking about. Our solution was to run that on a thread, so we had more control of that GUI program.
Here we can see our fall semester project timeline. The team worked on creating a 1x1 mesh, image processing, and mouse movement. Next. For our spring semester project timeline, we expanded to a 2x3 mesh, work on the GUI, and also work on touch interaction.
Here we will provide a little bit of a demo, where a video demo of where we are working on it. As you can see, on real time, I am working on the chalkboard as the camera is picking that up. And as soon as we trigger it, the program will capture the image. And then, as you see, it is upside down. So we'll have to correct that. It will flip it upside down and crop it out appropriately and apply the image processing. It will invert it to a black and white image with black words and a white background. So it's a little bit more similar to a typical note that one would hand out to the class. And then next, we will be implementing the touch interaction. As stated earlier, we were using a 4 clock cycle. When it detects a touch, we were treating it as within that 4 cycle. Is that if there is one touch interaction, it will treat it as a left click. And if it's all 4, it will be right click. And then if there's 2 interaction of touch within those 4, we'll treat it as a double click, which is the one I was having the most issue here. I am struggling here a little bit because of that. There were some voltage reading sensitivity issues, but I was able to successfully open the file that we just opened up. We just applied the image processing on. And just as a proof of concept, the image was a little bit blurry because the projector we were using, in order to fit in the mesh, we had to bring it closer, which made it out of focus. But as a proof of concept, when we focused it properly, as you can see, projecting onto a blackboard gives very nice colors and is actually very legible compared to just the white background. And it is very viable solution to project right onto a blackboard.
So after watching the video, we can see we completed image capture, image processing, output of various image formats. We also completed touch interaction with a Windows computer, and we met the cost criteria, making our product closer to $250. Next, as for future improvements, we increasing the consistency for touch interaction, PCB with fixed housing. We are also working on improvement of the GUI, hardware button implementation, drag movement for touch, and a system easy to install. Next. Here you can see a list of our project components, and with a total of $248.31. Next. As far as for code and standards related to our project, using the IEEE guidelines, we have standards for electronic power transformers, standards for high-speed serial interconnected bus, standards for electrical resistors, and standards for safety levels with respect to human exposure to electric, magnetic, and electromagnetic field. Next. For ethical considerations, we follow the IEEE Code of Ethics, where our impact with treating all persons fairly by making our product affordable, and we're trying to be honest and realistic and related to stating claims based on our project. We also use the NSPE Code of Ethics. Hold on. We just want to cite all sources to avoid potential copyrights and be transparent with our potential buyers. Next. So for our engineering complexity in an ideal scenario, everything we design will look great on paper and gets accomplished in a timely manner. Reality, it wasn't straightforward in practice, especially in times like this, where our team was affected by the current pandemic situation. It actually hit us when we were trying to do integration testing. We had 1 month to do it, but we had to prioritize our team members' health and couldn't really start until the 3rd week due to quarantine and safety protocols. So here also we have a disciplinary integration. Besides electrical computer engineering and structural analysis, we also created a mount where it can hold the board and the camera in place. This will be for demo purposes that we created it. Next. So as we mentioned before, an issue we ran into was the power supply. When we calculated it, the power supply looked good on paper, but it didn't implement well because we assume breadboards will be like will act like a wire. Also, the alignment, it was more difficult as we thought it would be. So, for so conclusion and lessons learned, we successfully created a prototype. We will work on the improvement of required for a more completely product. And as far as lessons learned, teamwork and communication is crucial for overcoming difficult situations. Importance of flexibility for mission accomplishment, and the importance of prioritizing teams' health and wellness. This is our references, and we can take any questions.
Thank you, guys. Thanks for this informative presentation. Um, any questions for the team? Okay, if not, then we can move on to the next presentation. I would like to introduce Vice Nade